Hello, this is the 2020 Adventium final presentation. The capstone team for this project include Caleb Burnham and Ariel Sievers. Our sponsors were Tyler Smith and Alex Marr, and the company who sponsored us was Adventium, with the project itself in development for NASA.
To see examples of this, we can consider the construction of CubeSats and that of a vehicle. CubeSats are essentially miniature satellites that are constrained by a size of 10 by 10 by 10 centimeters and a mass constraint of 1 1/3 kilogram. Their small size makes them an inexpensive option for academic study and amateur projects. However, this also imposes design restrictions. The weight of the material used in the CubeSat's construction might influence the number of electronic components available to use, or influence what types of connectors are available. When optimizing for a certain objective, the principle of least commitment design would avoid settling on a specific type of material before all options were considered. Now, this example might seem quite simple, however its usefulness becomes apparent when we consider more complicated objects such as vehicles with potentially thousands of design points. Any vehicle is going to be a compromise between a bunch of different dimensions, including speed, ergonomics, fuel efficiency, mass, and cost. A race car is going to be extremely fast, but that's going to come at a high cost with a negative impact on ergonomics and fuel efficiency. A commuter car might try strike a balance between all of these factors. However, the trade space is just simply enormous, and it's extremely likely that a designer or an engineer won't find the optimal design. This is where CAFMAD and our project come into play by trying to automatically analyze this trade space.
As you can see here, we have a solution, divided into 3 parts. Each part represents not only a step along the way of creating a trade space analysis, but also a widget that we would be creating. These widgets would be built using Angular to capture the idea of a modular web application. With this separation in mind, there is still a clear connection from one widget to another. The first part of the solution, dimension selection, would have the task of showing the user available selections from what is called a design space investigation. This is a file that specifies all parts and changes throughout the analysis, including available dimensions of variability for a particular artifact, selected dimensions and values entered by the user for their variance, analysis scripts the user may utilize during analysis, and more. The dimension selection widget allows the user to choose which dimension they would like to freeze or keep constant throughout analysis. The second part, analysis selection, has the role of creating steps for analysis. Each step consists of a script that the user is able to select and order in whichever way they'd like. Available scripts to use may depend on which dimensions the user did and did not select. After selection, ordering, and saving these scripts, there is the option of choosing exploration strategies. These are meant for the dimensions that were not selected, as a way to tell the program what to do with the rest of the dimensions during analysis. Once strategies have been chosen, the next step is the results. Results are what show after analysis is performed. This would consist of a graph of computed values from the analysis. Finally, the arrow shown between each widget is a demonstration of how the design space investigation acts as an input for one widget, is modified during that widget's process, and the output serves as input for the next widget. For our schedule, I will go over the user stories for each sprint, as well as how complete they were by the end of this project. Not much was planned for Sprint 1 besides setting up the project, including installing dependencies and learning the basics of Angular through their tutorials online. This was also the time for us to familiarize ourselves with the project and what was required. The second sprint is when we started working on the dimension selection. So we have the user story. As an end user, I want to input a URI to a design space so that I can choose a combination of dimensions of variability to analyze. This was mostly completed, although we did not implement an error message to display if parsing failed. The next story, which is about freezing dimensions and updating the other dimensions according to the relationships, was not implemented. We ended with being able to select the dimensions, but these selections don't affect whether dimensions may be selected, hence why the next user story is considered complete. Similar to the first user story, viewing results was mostly complete, but we didn't implement a message for failed parsing. As implied earlier, we were able to implement dimension selection, including selection of their variants. Sprint 3 was when we started work on the next widget, and that is for analysis selection. This is mostly complete since the widget does not produce an analysis specification file as originally proposed. We also worked on a solution toward the potential for displaying large sets of data, however in a concise manner, and this would be mainly for the dimension selection and also for viewing results and graphs. Finally, we had the results widget, which we added on for Sprint 4. However, the analysis widget was still being finished up from Sprint 3. Overall, the results widget would show the values computed from performing the analysis, and it would show these results in a graph. This also led to creating a service to handle selections for the dimension selections and the analysis selections. Next up, we will be demonstrating each part of the application as described in the solution, as well as give an overall explanation of what each widget does.
The idea behind the dimension selection widget is that this is the basic layout of our application. First up, we have the dimension selection widget, and right now it's empty, so let's change that by giving it a design space to consider. When that is entered, we find that there are 4 dimension variabilities in this latency investigation. So we can select the dimension of variabilities to consider. There's also a search capability, and also if there are significant numbers of dimensions, we can use this pagination. So we will save these and they will be used in the script analysis widget. Only some dimensions might be relevant for certain analyses. Going back to the car analogy, an analysis for the best type of tire might require information about the project's budget, the mass of the vehicle, and what type of axle it's using. If these 3 dimensions are selected, then the tire analysis script would become available in the analysis selection widget. Ideally, selecting a dimension of variability should allow the user to add constraints, ranges, or custom values. This might take the shape in specifying a maximum budget size, a potential range for the mass of the vehicle, and performing an analysis on only a single axle type. While our application doesn't currently have this functionality, our design should allow this to be easily extended.
The analysis selection, as mentioned, would feature the selection of analysis scripts. After dimension selections have been saved from the previous widget, we will be able to select scripts to run. These scripts tell the program how the analysis will be performed. Some scripts may be shown and not available to use based on the selections that you made from the dimension selection widget, and these unavailable scripts will be impossible to move around or reorder, so they can be hidden using this button right here. In the case that there are too many scripts to show on one screen, there's also a search option or a pagination feature. To select scripts, you just drag it over from all scripts to scripts to run, and when you're ready, you can just save selections. There will be an analysis steps confirmation screen where you can go back and reselect your scripts, or you can just click confirm. Once you click confirm, you can choose your exploration strategies. What shows here depends on the dimension that you did not select in the dimension selection widget. There's a stepping strategy, a try everything strategy, and a sampling strategy. So for power consumption, we can get either a sampling or a stepping strategy. So I'll just do stepping, where I'll start at 1, I'll end at 10, and I'll step by 2. When we click on Save, then it will show you a confirmation screen for the exploration strategies, which you can either go back and reselect, or you can click Confirm to go into the analysis. It should be easily reordered, and once saved, each script should create steps. Then, the selection of exploration strategies should be chosen for each step. The choice of stepping, sampling, or try everything strategy is available for exploration strategies. And the type of strategy available depends on the dimensions type, real, integer, or itemized.
The output of the analysis step is a regular XML file. Since we only have access to, finally we have the results widget, so we will give that a results URI. And this will become populated with the data points from the analysis. On the x-axis we have an enumerated sampling rate, and on the y we have an itemized processor selection. Hovering over any data points gives us the exact sampling rate, the processor, and the processor's latency. All of the data points are normalized, so they preserve their relative ordering. Larger data points will have a higher latency than smaller data points. Visually, this tells us that there is a significant jump for the 2 GHz processor at around 600 Hz, and for the 4 GHz processor at around 900 Hz. References of the analyses, not the analyses themselves. I had to input the results URI at the beginning of the last video. The results widget is listening for changes to this file and will automatically update itself upon input. It's doing a lot of work behind the scenes. The output file contains lists of dimensions of variabilities, their possible values, and a list of mappings between source design points and target design points. The source design points are the inputs to the analysis scripts, and the target design points are the output that we want to graph. First, this widget has to look at what type of analysis was performed and what shape the output data is in. This was a 3-dimensional dataset, with the input being one numerical dimension of variability on the x-axis and one itemized dimension of variability on the y-axis. The output consisted of a single numerical dimension of variability. This format allowed the bubble chart type to be used. While this is the only currently accepted format in our application, our use of modular components should allow this to be easily extensible.
At the beginning of this project, there was seemingly a lot of miscommunication between the Capstone team and the people at Adventium in charge of giving us access to the repository the project would be held on. This was initially about the paperwork that had to be signed. However, the issue got solved in about a week. Originally, as a team of 4, 2 of our members experienced difficulties with getting their accounts created, and then after actually gaining access to the repository, in total, the issue extended 2 to 3 weeks, which was most of Sprint 1. Angular was also found to be a difficult framework to learn among most of the team, which may have been partially due to most of the team not having much experience with the web frameworks in general. Plenty of time, the files given to us for parsing would have changed schemas, causing the program to stop working, which was usually solved within 0 to 2 days, but sometimes progress was slowed for tasks such as dimension selection. As mentioned, our Capstone team originally consisted of 4 members. As we split up for break midway March, with the impact of the coronavirus just starting to take effect in the area, the 2 members who faced issues with the delayed start on the project were also the same people who we lost communication with. Either way, work continued at a steady, if not a good, pace.
Looking back at our weekly report, we consistently put in a minimum of 6 to 8 hours of work per week per person. A lot of this was probably spent in JavaScript and TypeScript wrangling, but as a result has made us much more confident web developers. We each worked on a number of different components for the application and gained some experience in comparing different libraries, primarily in the style, where we compared Bootstrap versus Angular material, and in charting libraries. The original goal for this project was to allow the user to define custom constraints, ranges, and values, then to choose and order analysis scripts that were defined by the design space investigation data file. Then, the results would be displayed with support for a variety of different charts and data shapes. Initial difficulties with TypeScript slowed early progress, and the group's reduction to just 2 people made this goal unfeasible. So we settled on finishing the prototype with a check selection in the first widget, drag and drop selection and reordering in the second, and a display of results for the example data available to us. We tried hard to keep our application modular using Angular's components and services. This should hopefully make it easy for any future developers to pick up where we left off. As can be seen by the chart, a plurality of our time was spent programming, while the rest of our time was spent pretty evenly among the other components of development. Unfortunately, with only 2 people, it was difficult to find time for testing.
Next steps involve both the features we were not able to implement in the given time, as well as those that we were not able to with the fact that the XML files given to us contained only example data. For example, in Sprint 2, one of our user stories had to do with selection of dimensions, and depending on their variance, some other dimensions may become unavailable. Originally, for the dimension selection, we did also have selectable variance. However, this was changed to make analysis performance and the results widget simpler yet consistent. Of course, the application should eventually be made with actual and real data in mind. Some limitations were experienced due to using the example files, and this included a lack of constricting relationships among the dimensions or less parent-child relationships among dimensions as well. Although analysis steps were created in the analysis widget, they are still missing necessary values obtained throughout analysis. Currently, a step has only a reference to the analysis script, but exploration strategies still have yet to be added to the steps, as well as other properties requiring a value. The results widget had only recently been created, and there is still so much more that needs to be added for it. This includes finding a way to determine which of the computed values are most important to display to the user, and what the definition of important could mean. With the possibility of a large number of evaluated results, an option to filter through results should be applied, such as for adding constraints in an effort to maximize or minimize output. Overall, giving a clear idea of what the results are showing and what they could mean. Lastly, I would like to thank Adventium for giving us the opportunity to do this project. Although some difficulties occurred throughout the process, especially in the beginning, this turned out to be a really fun and memorable experience. Thank you.